So we have finished the one-to-many systems. Now we will go to our final module, which is a facility location problem. In fact, facility location problem is very important in many logistics applications. For example, if you have many customers, typically you want to serve these customers through some kind of facilities. For example, warehouses, depots, or retailer stores or hospitals, fire stations. So this kind of facilities typically will cover a certain amount of areas to provide service to these customers. Consider a very simple scenarios where the customers go to the nearest facilities. Then you will have this bunch of customers served by facility 1, and then this bunch of customers served by facility 2. Because building a facility or maintaining a facility is normally with very high cost, so the decision involving facility location is typically a long-term strategic decision. So this is different from the one-to-one problem where you just decide the schedule, which can be easily changed based on the demand, or based on the one-to-many system where you have a lot of routing decisions which can also change every day. The facility location decisions typically last for 5 to 10 years or even longer, so you may need to have a very careful decision. To solve a general facility location problem, the first question we need to ask is where can we open the facility? Although you may find a very good location, but sometimes you may not have the right to open a facility as you wish. Typically, we can only open facilities at certain locations, call it candidate location. After you have decided the amount of candidate locations, then you will ask how many facilities do we need. This is also a very tricky question. Definitely more facilities can have better service to customers because they are closer to the customers. Definitely open a facility is expensive, so if you open too many facilities, then your business may not be sustainable. So we need to find the best trade-off between the service quality and then the cost to maintain the service. And also sometimes the facility has certain kind of a capacity, so you need to decide the size or capacity of a facility. And then if you have a large facility, and your cost will be high and capacity will be high, if you can better utilize this type of capacity, you can generate more profit. But if you invest too much on the large facility, and then your service may also not be sustainable. We also need to ask how we allocate the demand. The example we just provided, we tell you like the customer go to the nearest facility. This is very intuitive. If you have a longer distance to travel, you incur higher cost. But sometimes, for example, the capacity may be full, and then you may need to assign a customer relatively far away to other facilities. So that indicates that the decision for the customer to the facility is not only determined by the distance, it's also determined by other customers' decisions. So we need to balance all these factors. We will provide you a bunch of models related to facility location problem. They may have different objectives or they may have different constraints. Their application typically can be applied in different fields. So let's see the first model. We call it set covering model. So the core idea for the set covering model is that every customer is covered, and also we want to minimize total cost. So this is intuitive. Set covering. We want to guarantee everything is covered, and also we want to minimize the total cost to achieve our goal. So let's introduce some notations. Suppose all the customers are indexed by I, and then they form a set called I. And then suppose all the facilities are indexed by J, and then they form a set J. So for example, if we have 5 customers, see this is I equals to 1, 2, 3, 4, 5. And then if we have 2 candidate locations for facility, then we have j equals to 1, j equals to 2. And then to characterize if a customer can be covered by a certain facility, typically this is given by the distance between the customer to the facility. Let's say we indicate aij equals to 1 if I is covered by j and 0 otherwise. Suppose that the distance from I to j is smaller or equal to a threshold, and then we'll think that the customer I can be covered by facility j. And also, we need to provide the construction cost or setup maintaining cost for facility j. We call it fj. This is a setup cost. And then we can have our decision variable xj. So if xj equals to 1, that indicates we open facility j and 0 otherwise. Okay, so know that the 2 set of binary variables. One is aij, indicates if customer I is covered by facility j. That's the parameter given to us. And then ixj here is our decision variable. So with all this, we can have our optimization problem, which is intuitive. We want to minimize the total cost to open all facilities, right? So if you open a facility j, you incur a setup cost fj. So it will sum up all the possible candidate locations to indicate the total setup cost. The less facility you open, the less cost you will pay. And definitely, we need to guarantee that every customer has to be covered. So for each customer, you may have different candidate locations. And the sum of the locations, if it can be covered, then you have aij is 1. So to tell if a customer is covered, you need to guarantee that for some certain j, your aij has to be 1. Definitely, if you have multiple coverage, it's okay. But you need to guarantee that at least one facility can cover it. So to capture this, if facility j is covering I, if aij is 1, and the facility j is opened, then this is good. That indicates I is covered by j. So we want to guarantee that for all possible j, you need to have at least one facility coverage. So here we have 1 to guarantee this happen. Remember, this is for every customer, all customer I. Okay, repeat again, right? So if you have customer I covered by facility j, given facility j is opened, then aij times xj will be 1. You need to guarantee at least one facility can cover customer I. So that means the summation of all this index should be at least 1. Okay, so we have our decision variable, which is our facility opening decision, which is 0 and 1 binary decision variables. So pretty simple. We have an objective that's minimize the total cost, and then we have kind of one constraint to guarantee the coverage. That's our set covering problem. So now let's consider a variation of the set covering problem. So in the previous settings, we guarantee that all customers are covered. So in reality, maybe this is too luxury. We may not be able to cover all customers. So this can give us a question. So if we cannot cover all customers, can we cover the most customers? So the reason why we cannot cover all customers is typically because we have a limited budget. So that indicates that to capture the limited budget, for example, we can consider that the number of facilities we can open is limited. So let's see this constraint. So previously all customers are covered. Now we need to make a decision on if a customer is covered or not. So we need to differentiate the customers at different locations. Remember, I indicates the customers. So let's see the number or the volume of customer demand at each customer location is indicated by HI, the amount at location I. And also we need to additionally make a decision on binary decision. So if customer I is covered, then we let di to be 1. And then if it is 0, it means we do not cover it. In this end, we can formulate the problem. We call it maximum covering problem. So we want to maximize our covered customers. So we want to cover a customer at location I, the amount at this location is HI. And then we want to guarantee we cover the more the better. But definitely we have some constraint. Let's see, the number of facility opened. Let's see, is bounded. Yeah, definitely we can have a variation such that the number of the total budget to open the facility is less than a certain budget. So here we just give the budget on the number, which is a simplified version of it. And also previously we have shown that the coverage. So if customer I can be covered by an open facility J, then Aij times Xj should be 1. So here we want to guarantee that if we choose customer I to be covered, Vi equals to 1, then we need to guarantee that at least one facility can cover it. But if we choose that Vi equals to 0, that means we do not need to cover this customer, and then constraint doesn't need to be satisfied. So this is also for all customers. And then our decision is our facility location decision, open or not. And also we have customer coverage decision, which is also binary. So you can see from the set covering to maximum covering problem, we kind of relax the decision on if we have to capture all customers. Some certain customers can be dropped, which captured by Z. Now let's consider another variation of the set covering model, which is center models. So in all the set covering and max covering problem, we have Aij to indicate the coverage. So that means if a facility can cover a certain customer, we will know it in advance, which is our given parameter. But sometimes we may not have strict coverage boundary, so that indicates that we want to find some certain decisions. We can try to minimize the coverage distance. So that indicates our Aij here will no longer a parameter, so this is no longer a parameter. So the coverage distance can be a decision. So let's consider the coverage distance, D, as our decision variable. To achieve this, we need to introduce another parameters, Dij. This is a distance from location J to customer I. Previously, this is all embedded in the coverage index Aij, but now we need to determine the distance matter. So the distance from I to J is given, and then we will need to decide Yj. So that means if customer I goes to facility J and 0 otherwise. So now let's see the model. So we want to minimize coverage distance D. Remember we have some given constraint. Let's say the number of facility is limited or budget is limited, the same. So here less or equal to P and equal P are the same constraint, because it always achieves the maximum number of facility to cover it. So here, because the coverage distance is not determined yet, so we need to capture a customer travel to a facility with a distance less than D. Remember, we have distance from I to J, which is D. And then we need to tell which customers goes to which facility, right? So let's see if customer I goes to facility J. That's why we introduced this assignment decision. If customer I goes to facility J with the distance Dij, then we need to guarantee this is smaller or equal to our threshold to indicate it is covered. But definitely the customer may not go to only one facility, So we need to find out which facility the customer will go. So we will introduce a constraint to tell us that the customer I will go to a certain customer J, but only choose one. So this is a choice model. Y is a decision variable for all I, and then you have all facilities to choose, and then you choose only one facility because Yj is a binary decision, the summation is 1. So only one Yij can be 1. The value to be 1 indicates customer I goes to facility J. So in this sense, we can sum up all this distance measure together because only one Yij is 1. That indicates the distance. So the same for each customer. So with these two constraints, we can guarantee that the customer assigned to a facility J, the threshold will be D. But here, remember, a customer can only visit one facility if it is opened. So that indicates Yij equals to 1 only when Xi, Xj is 1. So that means if you do not open a facility at J, you can never assign a customer from I to this facility. So that means this is for all customer and facility. Okay, so in summary, so this is the threshold distance. And then the first constraint tells us the budget for the facility. And then these two constraints tell us assignment with coverage. And the last one guarantee that the assignment feasibility. And definitely we have our decision, which is open the facility and assignment decisions for each customer. So in short, we have introduced a set covering problem. So the set covering problem, we try to minimize the cost. And then constraint is all covered. All customers are covered. And then we consider its variation, maximum covering. In the maximum covering problem, we max coverage demand. And then our constraint is our cost or budget. And then another extension is our center model. So in our center model, we minimize the coverage distance and also with a cost constraint. So in other words, set covering is kind of the stronger problem. We want to guarantee that all customers are covered. Sometimes we cannot achieve the goal because it's too expensive. So we can have max covering that indicates we want to guarantee the maximum number of demand is covered with a fixed coverage distance. Or we want to minimize the maximum travel distance that we can cover all customers. So sometimes because the number of customers in the center model is constrained by a value P, the center model, sometimes we call it P center model. Now we consider median models. So in the previous set covering model, maximum covering model, or center model, we kind of have a uniform coverage. So we cover or not, or cover with a certain threshold. That is typically helpful when we consider the scenarios with the worst case. For example, a hospital have to cover a patient within a certain distance, or fire station have to cover a residential area with a certain distance. But sometimes we may not need to equally treat all customers. That's why we can have our median models. So we just want to reduce the travel distance from the customer to the facilities. We don't need to treat them equally with a certain coverage threshold. So in this case, the problem becomes more flexible. So we want to minimize the travel distance for all customers to the facilities. Remember, at location I, we have demand HI, and then the travel distance from I to J is Dij. And then if customer does travel, that means we do assign customer I to J, and then this is the travel distance for customer. So we sum up all the customer and the facilities that can tell us this all travel distance. Want to minimize all travel distance. Okay, so definitely we have a similar constraint. For example, we guarantee that the number of facilities is equal to P, which is limited. And then we have customer decisions, Y, J has to be smaller or equal to J. When a customer can be assigned, there must be a facility opened, and also a customer has to be assigned. Okay, so this first constraint, limited budget, and then assignment feasibility and choice. Okay, and then our decision is definitely facility location, open or not, and the customer assignment travel from I to J. So because we have limited number of facilities P, sometimes we call this P-median model. So from the P-median model, we can further extend. We can have a flexible budget. Previously, we can have a certain number of facilities P, but now we may balance the travel distance and the facility setup cost. So the more facility you build, the higher cost you will incur, but the less distance you will need to travel from customer to the facilities. Call it fixed charge problem. For the fixed charge location problems, we want to balance the total setup cost. Remember, this is our objective in set covering model. This is the total cost to build all facilities. And also, we have a travel distance measure. We just introduced in our P-median model. Demand travel with facility J assigned to this customer. This is a travel distance. So here we have the setup cost and then travel distance to balance. So typically we will consider a unit travel cost. Let's say alpha to indicate the travel cost. And then we can sum the two costs together as our total cost. So we want to minimize the total cost. So in this way, our constraint for the number of facilities are now demonstrated in the objective. So our constraint will be easier. So we just guarantee that the customer assignment is feasible. We can assign customer to J once it is open, and definitely our choice model. You have to guarantee that for each customer I, you are assigned to a certain facility J. So your decision will be facility open decisions and then customer assignment decisions. And as we mentioned in the beginning, when you assign customer to facility, the facility may have certain capacity limitation. So in this way, we can further extend our fixed charge location problem with a capacity. So to achieve this, we need to define the capacity for facility at location J. Let's say capacity with capacity indicated by KJ. So in this way, we need to guarantee once we assign customer from I to J, the total demand does not go beyond the capacity. So the total customer assigned from I to J, this is for all customer I, for each location J. This is all customer demand. It has to be less than the capacity, KJ. And in a special case, when the facility does not open, that indicates the capacity is 0. So we need to multiply it by facility open decisions, xj. So this one, we can have our capacity constraint. So in summary, we have introduced two setup problems. First, we want to guarantee a certain coverage distance. So that indicates for example, we want to handle a hospital or fire station. So that guarantee a certain coverage threshold. We treat customer equally. So we have set covering model. So if we cannot cover all customers, we can have maximum covering model and center model. And then we further extend to cases where we can focus on the average performance of customer travel distance. So that means we focus on the aggregate customer. This is typically useful when we handle business. So we treat aggregated customer. So this one we further have our median model and then extend it to the fixed charge, or we treat the trade-off between the facility cost and then the travel cost. And also we can have our capacity fixed charge problem. So in this way, if you consider you are running a public service, you may choose the models with covering, or if you want to run your business with highest profit without considering the customer equity, you may consider the median model or fixed charge model.